Good morning, everyone. We are Design Team 5. We are working on TI's overcurrent protection design, reference design and study. Our facilitator is Dr. Win Lee, and our sponsor is Mr. Pete Semick.
I'm Stephen England. I'm Kenji Aono. I'm Joshua Myers.
And my name is Ryan Latterak. Alright, so what is overcurrent protection? Overcurrent protection is you want to, once there's a threshold current reached, you want some mechanism to switch off or divert power towards the load. Traditional methods of this are circuit breakers and fuses, and our advantages over these methods are that our design would be smaller in size, it'll be quicker and more cost efficient. Our sponsor gave us two applications. Our first application is overcurrent protection for a tablet PC, and our second application is monitoring the current in the cell phone and displaying it on an LCD. For our project, we wanted to look at different types of current sensing, if they were even feasible for our project, and advantages and disadvantages. So we looked at 4 types. We have using a MOSFET, which when we looked at it, some advantages were that it was really quick and would have been cost efficient for us. However, due to having a DC power supply, we would not have been able to switch the power off or on, so that wouldn't work out for us. We looked into Hall effect current sensing, in which when you push current down a trace on a PCB, you would have magnetic field created, and you could view the magnetic field through a toroid, and you could then find out what the current is going through the circuit and determine if you need to stop the current from there. For this, the disadvantage was that the toroid would take up too much space on the PCB, and it would be too costly for us. For the current transformer, we could have the idea is to isolate the current through the circuit using 2 inductors with coupling. However, with a DC current, we couldn't use inductors, so that was also out. And then our final idea was current shunt monitors, in which you have a current shunt resistor that a monitor looks for the drop across, and once it outputs a certain voltage for the drop, you just have to compare it. For that, we have low side and high side current shunt monitors, in which the low side you have the resistor from source to ground, but in order to use that, we would need a current transformer to isolate the current, and so we went with the high side current sensing, in which you have a resistor from the source to the load. And although there's a bit of an insertion loss, when you use a really small resistance. And here's Steve to talk about application 1.
My name is Stephen England, and I'm going to talk about the first application, which is for the tablet PC. The purpose of this is to design an overcurrent protection system that will switch off power to the load if it draws more than 1 amp of current. If it draws more than 1 amp of current from the source. The source is going to be a lithium-ion 3.6 volt, 6.75 amp hour battery. The priorities for this application were a small size so it could fit inside a small tablet PC. It has to be low power to minimize impact to the rest of the tablet PC system. And it needs a fast speed of shut off so that if the load were to draw too much current, it wouldn't damage the PC too bad. And it has to be low cost. Alright, here's the block diagram of an initial design idea. Here's the 3.6 volt battery, and here's our TI-9A138 current shunt monitor, and that's going to measure the drop across this resistor and output voltage based on that. And then another input to the comparator is going to be voltage divider, which is already a set voltage, and it's going to compare those two based on that, which right now This is set at 1.8 volts, and this is designed to output 1.8 volts if it's at 1 amp. So if this is higher, it's going to output a low voltage here. So, and then when that outputs a low voltage, the TI load switch is going to open and cut power to the load. Here's the part justification for the first application. We chose a TI INA 138 current shot monitor mainly because it had a variable gain, which for designing all we had to do was change a couple resistors to change the gain, and it allows you to change the gain from anywhere from 1 volt per volt to 100 volts per volt. One issue with this is that it has a high input offset voltage, which could affect the accuracy of our design, because when we're working with a small drop across the current short resistor, since it's such a small value, that 1 millivolt, which I think it was, might affect the accuracy quite a bit. So we're looking into maybe some other options once we test that and see how it works. Next is the TLV3491 comparator. The reason we chose this is because it's this fast shutoff speed, it's 6 microseconds, and it has very low power consumption. It takes microamps for it to be powered up. Next is the power switch, the TBS2033. This works well for our design because it's rated at 2 amps, so it will allow over an amp of current to pass through it, which we need in case 1 amp is ever drawn from the load and use the switch. And it's high enabled, which for our design is how it works. If the comparator is outputting a high, the switch is going to remain closed. Next, Kenji's going to talk about the second application.
I'm Kenji Aono. I'll be talking about application 2, which is current monitoring inside a cell phone. And in this application, we don't need to turn off power if it exceeds a certain threshold, but we are dealing with currents down in the 7 to 100 milliamp range, which is less than 1% of our previous application, so accuracy is key in this one. And we are going to display the current being drawn to an LCD so the user knows how much current is being drawn. And our voltage source varies from 3.3 volts on a full charge to 2.7 volts when the battery is near depletion. And here's our block diagram. Again, our power source is up here. The variable load would be our cell phone. And we put a current shunt resistor in series with the two so we can have a voltage drop across it when there's current flowing. And we have current in the 100 milliohm range, and this is a 10 milliohm or 25 milliohm current shunt resistor, which gives us microvolts. So we need to amplify that using a Texas Instrument INA333, which is a very precise instrumentation amplifier, which has about 10 microvolts of offset, so this should allow us to get accurate readings. And we take the analog signal that's been amplified and we convert it to a digital signal using a 16-bit delta sigma converter, and that signal gets sent to our ECE480 microcontroller, which is then displayed on our LCD. Here's a little bit about the ECE480, why we chose to use it. First off, it's very low power. It uses 300 nanoamps in standby, which it'll be in standby most of the time, and 220 microamps per million instructions per second. So if we run this thing very slowly, it doesn't have to go very fast, we won't be drawing too much power. We chose to use an external analog to digital converter because we won't know what sort of capabilities a cell phone's processor might have. So if we offset the analog to digital conversion to an external chip, we won't have to worry about that in our final designs. And the final design is to port to an OMAP, which is a pretty popular processor inside cell phones such as the Motorola Droid X. The ECE480 is programmed in C or assembly, which can be ported almost directly to the OMAP processor with very little effort. And this processor also comes in various sizes, so we can test using a regular DIP processor, and then in our final design we can switch to a very small scale and solder them to our PCB. And here's Josh to talk more about the PCBs.
Hi, I'm Joshua Myers. I'm going to talk about the PCB design for this project. So first of all, I'll explain why PCBs are so important to this project. And they're important because traditional testing methods such as proto boards add parasitic elements to the circuit due to the wires and the metal inside the boards themselves. And for our applications, our current sensor requires high accuracy and precision, the current is measured through a series of a shunt resistor, which is approximately 25 milliohms. So any kind of extra series resistance due to a proto board is going to throw off the reading quite a bit, and it's going to be pretty much impossible to test. So PCBs allow us to avoid these issues, allow us to have less interference, and traces provide a low resistance connection for the parts. So there are three primary PCB fabrication methods. First is CNC milling, which is what the ECE shop does. It's very accurate, however, it has a pretty low resolution. You can only go to about 300 microns. So that's not going to work for our design because some of our parts are on the scale of about 200 microns. The second possible fabrication method is chemical etching, which is a higher resolution of about 150 microns. It's inexpensive and it's very fast. It can be done in about an hour. And then the third option is professional fabrication, which is the highest resolution accuracy, but it's pretty expensive and it can take 2 to 3 weeks to get the design done. So we decided to go with chemical etching for our initial prototyping, and then in the end, towards design day, we're going to go with the professional fabrication for both our designs. So real quick, I wanted to run you through design we finished already for application 1 using chemical etching. So first, of course, you design your PCB using a program such as Express PCB, and you get something like this. Then you invert the colors and print them out on transparency, which is called a mask. And then you hold it up to your substrate and expose it to UV light, which will allow the parts that are see-through of the mask to be etched onto the PCB. And then you wash the substrate with a chemical bath to remove the extra mask everywhere where it's darker. And then you etch it with another chemical solution to etch the copper in the place where it's desired, so you get a final design that looks like this. So one thing our sponsor really mentioned is he really wanted us to work on a reference design for TA of what the optimal PCB layout is for something with such low resistance. So some things he wanted to experiment with were optimal parts placement. If the difference between the current shunt monitor and the op amp is like 5 millimeters versus 10 millimeters, what's the difference in the interference between them? And trace size is also another thing. As you can see, the resistance of a trace is tuned by this, so if the length is increased, the resistance is going to increase. If the width is increased, the resistance is going to decrease. So we need to experiment with different lengths and widths to get a good trade-off between the resistance. Another thing is the corner angles on the PCB. If you have 90-degree corner angles, then there's going to be more interference in your circuit, so we need to experiment with rounded edges and 45-degree angles. And finally, we're going to experiment with layers and vias and how they affect the resistance of the overall circuit. That's it. Any questions?
Any questions from the class? Everybody's tired this morning. All right, I've got 2 questions. They're non-technical, but still, are you guys planning on entering this in the analog design contest? Have you thought about that?
Yeah, we have I think we already turned in the form because Pete Semming sent us the information. So
Okay, yeah, you really ought to, because there's very little extra documentation required other than what you're going to do for the class, and it's the type of design we're looking for. It's really a good candidate for that contest.
The only thing with that is that there are actually 2 parts to that. There's the national level, which we're not really allowed to enter because we're sponsored by TA, and then there's local level. So I believe our team and then Team 6, which is also a TA project, are both automatically entered into those.
Okay.
So I think it's just us 2 competing against each other basically for that.
I don't know if Team 6 is going to have analog parts. Well, we'll find out when we hear them. Yeah. All right, very good. I've got a couple of comments. I'll send them out by email to you later today. Good job for first up Monday morning after the clock changes.